So let's start out with a little bit of history. Some of it's trivia, some of it's actually pretty relevant. On the far right, looking all the way back to 1986, this is when the U.S. decided to, well, actually two people. One person's name was Larry Smart, who founded the National Center for Supercomputing Applications in Urbana in Chicago, outside Chicago. And the other one was Sid Caron, who formed the San Diego Supercomputer Center, which is where I spent a reasonable part of my career. So back in '86, prior to this, people were doing classified work on mainframes. These were the supercomputers of the day. And if you were a researcher and had some large data, large compute problem, you had zero access to any kind of facilities. So these guys went to the National Science Foundation and basically created the very first non-classified supercomputing centers. NCSA, people probably should know, they basically invented the internet. Mozilla came out of there, so the web was basically born out of NCSA. Looking forward, around 91, late 91, first version of Linux came out. It was just kind of a place marker, so you kind of know how old this stuff really is. And then in about 94, the NOW project, NOW stands for Networks of Workstations. And this is a project led by David Keller out of UC Berkeley. It's the Millennium Group. A lot of people know about Beowulf and Beowulf clustering. These guys actually predated them. They were doing everything on what was a commodity at the time. So it was actually SPARC 1+ systems. That was commodity. Linux wasn't really there. PCs weren't really appropriate for servers. Ethernet cards, Ethernet chips definitely were not on the bubble boards. And then back in late 99, this is the group that I started my career in cluster computing with, is the Rocks project released its first version of software. What this was a software stack to allow you to cookie cutter stamp out high performance clusters. Meaning you had a set of servers, 6 servers, 100 servers, several hundred servers, and you could literally just put in a piece of DVD media, type in a little bit of information, and you have what we used to call a supercomputer center on a disk. It's actually not quite true. The very first version was actually a floppy. That's how old this is. And then fast forward a little bit. That's 2004-ish. The Google MapReduce paper was published. A few years later, we had the very first release of Hadoop. And today, of course, 6 years after that, we're at Hadoop 1.0. Our company, StackIQ, was founded in 2006. And we were basically founded to commercialize the open source Rocks project. I'll go back to the Rocks project a little bit. Is prior to this time, if you wanted to build a cluster in '99, you were doing disk cloning. You were taking months to build anything. It could take 6 months to build a system. You were doing CF Engine on top of that, and it was just ad hoc cluster management, and it was so unstructured and so error-prone that it was very, very difficult to get anything going. And that's what created projects like Rocks, is trying to remove these errors. And I hope you'll see a lot of the same. The main theme of this is a lot of the same issues that we had back then, or the issues we have now. It still takes months to build a new cluster. It's a very, very difficult thing to do, and it's very hard to manage large sets of issues. So I jumped a little bit ahead, just kind of go back to step 0. What is a cluster? When I'm saying a cluster, I'm just talking about a bunch of machines managed by one or more management nodes. In Rock speak, we call that guy front end. He's the guy that's connected to your external network, be it corporate LAN or internet. And you have a back-end network, and this is where all your workforces are. So you could have a few dozen machines, a few hundred machines, a few thousand machines, all being managed by this one guy. And then, of course, you could add application networks. You could add InfiniBand, you could add 10 gig, you could add extra public-facing Ethernet. I mean, this architecture is a web farm, it's a Hadoop cluster, it's a computational cluster, it's what everybody building clusters is doing. Everyone is building a variant of this. So where does Rocks really come from? So we will quite a bit of philosophy. We've been around for 10 years or so, and we're all about scalable IT automation. We're really just trying to make it easy to bring up a system that works out of the box with reasonable defaults and make it so people can then extend it and customize it afterwards. So when I say easy, what does easy really mean? We're trying to make it easy for you to get your work done. The text I really like on this slide is, it should be simple. Just getting your work done should be simpler than the work you're trying to do. So, end of the day, we're trying to process data and get results. That's a hard job. Managing that infrastructure should not be a hard job, and it is today. It needs to be easy for novices, people working in hours. It also needs to be easy for experts to extend and customize and build exactly what they want. You shouldn't have to be an expert to build automated complex systems, and you should be able to build whatever you need. High performance computing, big data, scalable web architecture, clouds in hours. So what do we really do? We're trying to make everything for infrastructure automatic, repeatable, and reliable. And I come out of a university environment, so I'll be a little academic here, we're really trying to do science. And if you can't reproduce the results don't exist. So you take that all the way down to the infrastructure. Your infrastructure has to be reliable, consistent, completely automated, get humans out of the way because they're the most error-prone and most expensive part of the system. And it needs to be repeatable. So that's really what we're trying to do. So automatic-wise, end of the day, people do not scale. Repeatable, nothing is homogeneous. A lot of effort today is spent managing sets of machines where people are playing with Ethernet chipsets. They're trying to resolve name-meter networks. They're trying to resolve these terrible, trivial differences on their hardware. And because they aren't abstracting it and managing at the right layer, these differences are exposed. And what Rocks really does is hide these differences and runs on everything. So some of the methods, we really optimize for speed. One off guy, and this is the standard use for people building clusters today, people that are Rocks clusters today, one off guy should be able to manage 500 to 1,000 servers. We've been into data centers where the ratio of people to machines is 1 to 6 or 1 to 32. It's not that it's expensive, it's that on a large cluster you have a team of people doing random different things to your infrastructure, so it's very hard to keep things going. We manage entropy by a very different method than most people. Rocks is really about managing all the bits, and we're talking about philosophy, we'll get into details in a little bit, but Rocks is really about managing all the bits, all the way down from the kernel, all the way to the application. And because we're managing everything and deploying stuff in an atomic chunk, the quickest way for people to really get their infrastructure working and correct mistakes is to just start over. And that sounds really scary. We could build 1,000 machines in about an hour. We could build one machine in 10 minutes. So when you start having failures and you suspect library differences or some user did something crazy to the machine, kernel crash, and you swap out a disk, whatever, blow the machine away and start over. It's fast. Okay, so why does this really matter? I said at the beginning that back when we first started doing cluster computing, it was taking people months. 3 months, 6 months, or it's taking worse at these data centers, just to deploy anything. And even today, we're taking months to deploy things. So, old hat, everybody knows Moore's Law. Approximately what it says, basically the number of transistors that can be placed on a wafer doubles every 18 months. Is it 18? Is it 2 years? I don't know. I mean, this is ballpark. So that's really what Moore's Law means. But what does it really mean for people that are buying stuff? It means that your hardware just lost half of its value every 1.5 years. That's a scary thought. That's a scary thought when you have hardware sitting on the dock and not being used. So let's really look at this, because this is significant. What we're looking at is the green slope is just the value of your hardware over time. Starts out at 100% of base zero. Very quickly, by a year and a half in, you're down to 50%. So this is just kind of hitting you over the head with what Moore's Law really means. So if you're taking 6 months to get your work done, you just threw away half your money. So you say, well, it doesn't take you 6 months to do something. If it takes you 3 months, that's still 10% of your investment. People are spending hundreds and millions of dollars on hardware. So 10% is a significant number. 50% is a very significant number. And kind of one other takeaway of this is, after about 3 or 4 years, just throw your hardware away. It's not worth anything. So the real moral is time is money. And I'm kind of picking on DevOps, but I'm not really. But the real takeaway is DevOps is a waste of money. So if you're spending this time tinkering with your hardware and trying to patch it and build it slowly, you're doing the wrong thing. So time for a little video. Back in 2003, there was a show called Supercomputing. I think this one was in Phoenix. And the Rock, this is all showing Rocks, open source, building a Red Hat computational cluster. And what you're seeing is going from a group of guys taking hardware off the shelf. There's absolutely nothing installed in disks, and doing physical cabling, installing the management node, and pushing out a software stack and running applications as it's going. So kind of a fun PR stunt. When we did this, we actually did this with Sun Microsystems. The guys in green are from Sun. The guys in yellow were us at the university. And we approached several vendors with this idea, saying we're just going to build a cluster on the fly because everyone else is spending months to do this. So we're just going to show up, do this dynamically, and it scared the crap out of it. No one really was sure we could even do it, but it worked. So the guy at the console is managing the front end, installing the software, so an hour in, half the cluster was actually online and running. And you could see one guy who was quick talking to somebody asking questions, interrupting the process. And to show you it was a real demo, where is it? We thought we were done, and then we actually had a hardware failure. So this is a small cluster by today's standards, only 128 nodes. So yeah, an hour and a half in, we had a failed node. And as I said, we actually started to diagnose it on the floor, and just the quickest way to fix it is just yank it out and replace the node. Yeah, so an hour in, this thing was up and running. If people want to know the details, it was running super early version of Rocks. It was running SunGrid engine, and it was doing link pack benchmarking, so just standard exercise in the hardware. Okay, so to give you a little bit of philosophy of what we're trying to do, so let's talk about how this thing really works. So when you're first building a Rocks cluster, step one, burn your DVD media, put it into a front end, and it's going to do a complete install of Red Hat or CentOS. And it's going to look just like a Red Hat install, actually fewer install screens. It's going to ask you what your private network is, what your public network is, other stuff like that. And you just build it, you choose your roles, we'll define what a role means in a little bit. And then you just go. So you launch your management interface and you start adding back-end nodes. So when you're first installing the front end, it takes about 45 minutes to build the individual front end. And then the back-end nodes, what they do is you just turn on a node. You turn on a node, tell it to network Pixie boot. It's going to get an IP address from the front-end DHCP server, it's going to download its install kernel, and it's going to start pulling down packages and installing itself. It's Red Hat Kickstart. It's for people that know Red Hat. It is Kickstart, but there's a lot on top of it. It's all abstracted to an XML framework. It's all database driven. It allows you to build a large set of heterogeneous nodes, and more significantly, or maybe as significantly, as they're installing one node, that node is actually serving out data to other nodes. So you can install in parallel. It's not this kickstart a node, wait an hour, kickstart another node, wait an hour. It's all doing stuff over HTTP. It's highly scalable. The only caveat for bringing nodes up the very first time is you need to turn them on one at a time so you actually get a mapping of a name to a location of the machine. If you don't care where your machines are, turn everything on and just be on. So how do data centers really work today? This is more or less the process everywhere. Sometimes it's one group, sometimes it's many groups, sometimes it's more groups that are shown here. But the first step is really you get a bunch of hardware on a dock. Somebody has to go in and install minimal OS. Maybe it came from the factory that way, and you are ordering enough hardware so you can actually specify what your vendor does for you. So somebody has to get BIOS set up, OS installed on the machine. Next step is to configure the OS for what you need, possibly install patches. Lastly, get your application going, configure your middleware, etc. And then finally, it's handed over to users who still need to do their own configuration. So this is really the goal of Rocks, is that entire step of bare metal all the way to application is one chunk. That's all controlled. It can all be managed by one person, and it's predictable. So how do we do this? Rocks is not just a monolithic stack. We have something called roles. We are riffing on the name a little bit. It came from the open source world, so forgive us for riffing, just like Sun did with Java. A role is really, it's a meta package. It's a set of packages that go on a machine, and a set of scripts to install it. This sounds a lot like C Engine, it sounds a lot like Puppet, it sounds a lot like Chef, and it has a lot in common with them. It predates many of those, but it has a lot in common. The biggest difference is we have a management node that has a database that knows everything about the cluster. We know the network, we know what roles, R-O-L-E, a machine is supposed to be having, it's supposed to be what roles the machine has. We know the size of the cluster, we know what disk partitions should look like. We really know the entire system layout. So you're not just doing C Engine and trying to configure at any point. We know the cluster. So a role is a set of packages that might go on a machine, and it's a set of description that might need to run. The really interesting thing about a role for us is you get this role, this set of meta packages correct once, and it works on every cluster because it's all database driven. If I have a role that says this is how you build a Hadoop cluster, and we get it right, and I give it to you, your cluster database looks different than mine, and the role's just going to work. Some examples, we have at the kind of lower level of the stack, and drivers and stuff like that. We work closely with Dell and have a Dell role which has their versions of Ethernet drivers, has some of their management tools, etc. Have a role that does CUDA, so OpenGL has NVIDIA drivers. We obviously have a role for Hadoop, which Tim is going to be demoing. We have a role for CentOS, which is pretty different because up till now we've been talking about managing Red Hat CentOS machines. And this is actually just provisioning clusters of hypervisors. So it's more than just, the tool is very extensive to work with, but we busy focus today. So we have a nice user interface, but we also have a GUI for people that, we also have a command line interface for people that really need to work at that level. The point of this slide is really that there's a very, very regular syntax that's just like managing a switch that lets you control what all the machines in your cluster are doing. Everything is SQL based. You back up your cluster database, and you have the entire set of your cluster. So the entire state of your cluster can basically fit on a block. Okay, That's a brief overview of kind of the philosophy, where we come from, what problem we're trying to solve, and Tim's going to walk you through an actual demo of this.
So Mason explained the background of Rocks and what it means to infrastructure management. I'm going to focus more on Rocks as a Hadoop management platform, which is what StackIQ has been focusing most of its energy on over the past couple of years. And I will start with a quote from Tim Cook. This was at the end of the iPad announcement. He talked about Apple being the only company in the position to deliver the kind of innovation on the iPad because of the tight integration between software and hardware. Apple's building a known platform, which gives them tremendous advantages over their competitors, like Android. There are many similarities with Rocks and how we're managing Hadoop. Every other management system is building on top of an unknown platform. You're patching or changing an existing environment that the management system has no knowledge of. With Rocks, because we're doing bare metal provisioning going all the way down to the OS, all of the Hadoop management tools we're building are on top of a known platform, which allows us to innovate very quickly in this space. So what's the problem we set out to solve when we looked at building Apache Hadoop management tools? Apache Hadoop doesn't have enterprise class management software. We already have the best cluster management software in the world, so we spent a bunch of time tightly integrating Apache Hadoop. I planned that for the show. That's my explanation part of my voice. So complete Hadoop management. What does it mean when we say we're managing Hadoop? We're managing everything from the operating system, we're doing disk management, we're doing data management, and going all the way up to HDFS and MapReduce. So from the OS all the way up to the application layer. And Mason already described a number of our advantages, but a little bit on how they apply to Hadoop. 100% automatic configuration, so we know we're getting a known good Hadoop stack every time we do a deployment. We're managing all Hadoop components, so we do this both through a web GUI and through a powerful verb-based command line that I'll demonstrate. Running on heterogeneous commodity hardware is a big deal. There are some hardware vendors that are working on similar solutions, but they're specific to their hardware. Rocks works with heterogeneous commodity hardware of all types. And then being an extensible platform is also incredibly important. Hadoop does not sit in a vacuum. Most Hadoop clusters are sitting alongside traditional data warehousing solutions, or we can see a number of users running high-performance computing, Hadoop, and even private cloud jobs on the same infrastructure. Rocks is extensible and can manage every type of platform, not just your Hadoop cluster. Some real high-level comparisons between Apache Hadoop with Puppet versus Apache Hadoop with StackIQ Rocks. We get this comparison all the time, but Puppet is really just a small subset of what we do. It is extensible. You can do Hadoop provisioning with Puppet. They have a graphical user interface, but it's only for managing your infrastructure. It's not for managing Hadoop. Whereas Rocks goes all the way down to bare metal. We do cluster monitoring, we do cluster management, and then we do specific management of the Hadoop stack, managing the components inside of Hadoop like HDFS, MapReduce, Hive, HBase, Pig, etc. All right, I'm going to show one more quick video so you guys get the idea of what a Rocks install looks like. This is just the initial provisioning process. What you're going to see here are screenshots that would basically match what Greg and Mason were doing in the SCO3 video you saw earlier. This time we're going to be looking at the screen to see what's actually going on. This is a cluster in our lab. It's just 3 nodes. We're going to start out by inserting the DB into the front end. Then you'll see a boot screen come up that asks you what you want to do with that particular node. And in this case, we're going to type build to let the system know that this node is going to be a management node. You can get the stack from StackIQ.com. You can download the complete ISO. We also have, if you stop by our table, we brought some pre-built DVDs with us if you want to take one home and try it out. So we're booting off the DVD, typing build. It's going to do some automated hardware discovery with the kernel. And we're going to click on a button that says CD DVD-based roll. And this is going to allow us to select all of the modules that we want on this particular cluster. We would also have the opportunity to insert additional DVDs or install over the network. In this case, we're going to select base, OS, the Rocks core, and MongoDB, Hadoop, Cassandra, and the HPC link. When we hit submit, it'll build the distribution. After we hit next, we're going to punch in site-specific information for our cluster, things like host name and IP addresses. I'm going to make this go a little bit faster. So we're punching in a private network configuration, public network configuration, group password, pick our MTP server, and then do disk partition. We're going to select auto instead of manual. Then we hit next, and those are all the manual steps that are required to set up your management node. The bits will now copy to the front end, install themselves, the front end will configure itself. This is the process that takes about 30 minutes. The video fast forwards through the install. And after this completes, the front end will reboot and it will be ready to add back-end nodes. We'll quickly show that process. You'll see it's running CentOS. That's because we chose the default OS role in the distribution. That could be replaced by Red Hat or other Red Hat light versions of Linux. We're clicking on Firefox to load up the Rocks web console. And the first thing we're going to do is click on Discover after we log in. And here's where we start adding back-end nodes. Again, in this case, we're just doing 3 nodes, but the process would be the same if you're installing 100 nodes or 1,000 nodes. We're simply powering on each of the machines. They're set to PC first. You can see the MAC addresses have been captured here, and assigned IP addresses and host names. Now what we're visualizing here is the Rocks Avalanche installer. Mason briefly touched on this earlier. Rocks is a parallel installer that was kind of inspired by BitTorrent, where we're doing peer-to-peer package sharing across node during the install process. That's what allows Rocks to scale at hundreds or thousands of nodes and do complete bare metal provisioning as the central management process. The only other thing that we've seen in the market that's similar is an internal project at Twitter called Murder, where they're doing peer-to-peer package sharing for change management. But we believe we're the only ones who are doing peer-to-peer package sharing for bare metal installs. Now the cluster is up and running. I'm clicking through Rocks attributes, and we'll see this live in a moment as long as the network holds up. And a quick view of the monitoring screen. Move on. So that was the initial cluster install. We selected the Hadoop role, but we haven't told the cluster yet that we want to actually run Hadoop. So now let's talk about Hadoop management in Rocks. We did discovery of nodes, we did the Avalanche install. This is Apache Hadoop on the command line. I'm going to skip these slides for now. Here's Hadoop management from the GUI. We click on the Hadoop management tab. We select create Hadoop instance. We're going to start in this case with HDFS. We're allowed to select our data nodes, name node, secondary name node, and then simply hit create, start. And now HDFS is fully provisioned and managed on your cluster with rational defaults that were discovered during the initial install process. All right, let's flip over to live system. So this is a demo cluster in our lab. Current state of this cluster, we're cutting to the end of the video. So bare metal cluster with the initial rocks installed, no other prerequisites, no other software has been installed or configured. And we have an incredibly slow network. While the web page is loading, I'm going to do a couple things. I'm going to say rocks list roll. That's going to show the list of modules that are installed in this cluster. And then rocks list do, showing that we haven't done anything to set up to do at this stage. Come on. That looks a little better. There we go. All right, so we're going to click over to the New tab. We're going to go with HDFS, create new instance. Let's call this big HDFS. By default, the name node is the front end of the cluster, but you could select any node as your name node. Secondary name node by default is the first node in your cluster. Again, you could select anything here. And I'm going to select all the back-end nodes, but it's an important note. Rocks is fully capable of managing multiple HDFS instances, multiple MapReduce instances on a single cluster, or even doing one MapReduce instance across your entire cluster and then multiple MapReduce instances layered on top of that environment. Click Create. And what's happening here is all of the Hadoop configuration files that are normally created and configured by hand. Rocks is looking at the Rocks database on the front end, looking at all the hardware information you've discovered about your cluster, and creating site.xml, creating the HDFS specific config files, HDFS specific variables, and then pushing those files across your entire cluster. And then we can click Start, touch to start the service. Okay, the Hadoop instance has been started. I'm going to very quickly do the same thing for MapReduce. Okay, I'm going to start MapReduce. Okay, now we go back to the command line just to show that it's actually up and running. We'll start with rocks list 2, which is our command. Rocks list Hadoop name equals, let's do big HDFS. Give me an idea of some of the variables that are written to the backend nodes during the install process. And then let's real quickly run rocks run host. This command just runs a SSH command across the entire cluster. And we're on JPS, that's Java PS, to show that Hadoop services running across all your backend nodes. Build and manage a Hadoop cluster using Rocks Cluster. Back to the slide deck. I think I have 2 or 3 more slides. We continue to move farther up the stack in terms of management tools that are specific to Hadoop. One of the things you'll see soon are graphical representations of rebalancing and data from the job tracker. Also going to allow you to change Hadoop specific attributes from the Rocks GUI. And we already did that.